It has been said by some people that these problems in metallurgy that we've been looking at are all accentuated or all contained in joining of metals. I think this is probably so. We find that there are two major kinds of joining that we would do with metallic materials, and that is we join materials with fasteners. This means rivets or bolts, but we also join materials together by another technique, which means a metallic bond between the materials. And actually, in this particular way, we have a number of different kinds of welds or joints that we can make. Now, when we look at corrosion in the next lecture, we're going to talk about a little bit about fastening things together with bolts and rivets and such things. But today, in this lecture, we want to look at joining metals together by devices that involve metal connections that are continuous, not discontinuous. And so, for instance, we're going to look at soldering, brazing, and welding. When we get to welding, we're going to find out that there are actually two broad classifications of welding. We can do solid-state welding. That means that we can not melt the material. We can actually cause the metal parts to be welded together, having never melted them. And we can do a liquid phase melting and welding together. So we have all of the problems in solidification that are attendant to that with us. In fact, we have problems of coefficient of thermal expansion, quench rate, solidification rate, segregation, anything that you want to name as a problem that you would have in any operation. If you're doing a liquid metal welding operation, you're going to have that problem with you. Not only that, but you find that you can actually change the alloy that you're working with if you're not doing your welding job right in some cases. And so in this particular field of joining, we have sort of two crafts that have been developed. And one craft is a real art, the art of doing the welding operation, or putting things together with metallic junction. And the other one is understanding what goes on with that weldment or with that fastening. So what I'd like to do is to show you some of the techniques that are used for welding and talk about them. But principally, I want to talk to you about the metallurgical problems that are attendant to the welding problem or the joining problem. Now, I'd like to start, first of all, by disposing of the low temperature methods of joining materials together. And this is in soldering. Soldering means that we're going to join two materials together by wetting the surface with another metal. So if I have a piece of steel that I want to join to another piece of steel, and I do this by using a low melt material that will not cause the steel to dissolve or melt, I have to have a low melt metal that's going to wet the steel. And if it wets the steel when it's in the liquid state, then when it solidifies, it will join the two pieces together. Before we even look at what we would do if we were to do a regular soldering job, let's look at some of the no-nos or some of the things that we are told that we can't do in soldering. Like, for instance, I am always asked if I can solder aluminum. And I tell people, yes, I can solder aluminum. And if it's someone that has tried real hard to solder aluminum and not succeeded, generally you have an argument with them. But the situation is that you look at the thermal equilibrium diagram of the materials that you want to solder together. And let's suppose I look at the thermal equilibrium diagram between aluminum and tin, I find out that tin is completely soluble in aluminum in the liquid state. If I get the temperature high enough, I can get aluminum to dissolve in tin or tin to dissolve in aluminum completely. Well, if I can do that, that says I certainly ought to be able to wet the surface of the aluminum. But the aluminum has a tenacious oxide film on it, impossible to break almost, and therefore I have to use something to break down that particular oxide film before I ever get it to be wetted with the tin. Could I play a trick on it? The answer is yes, I really could. I could take, say, a pool of tin over top of a big body of aluminum, just heat the aluminum up until the tin is molten, let's say at 490 degrees or something like that. Stick a probe down through the molten tin and scratch the aluminum, break its surface. Since there's no oxygen to combine with the aluminum at that particular junction, the tin will wet it. And having broken the oxide film in one point, I could easily scrub it away everywhere else, and I could put a layer of tin. I could cause a layer of tin to be wetted onto the aluminum surface. I could do a second piece of aluminum like that. And then if I put the two together, all I've got to do is achieve the melting point of tin, then let it solidify, and I have it soldered together. Now, obviously, we're not going to take that much time to do it, and a better way would be to get a flux or a chemical that will dissolve the oxide film, at least momentarily, and allow us to penetrate that particular flux to deposit on the surface the tin. So it's very easy to solder one material with another material if, in looking at the equilibrium diagram, you find that in a liquid state they're completely miscible. Well, you would want to then say, look at the temperature series just to see what melts where, and you would wind up with a thermometer, so to speak, that looks something like this. And all we've done is arrange now the metals in order of their melting temperature for the alloys and the metals, and we start at the bottom at a very low melting point material. Actually, we could start all the way down with mercury if we were going to operate below that particular point, and we'd come all the way up with gallium and indium and metals like that. You'd say, well, they have no use there. It's too low melting, and I never want to use that as a solder. But the fact of the matter is, indium is one of the most beautiful materials to solder with you can find. It wets just about everything, and in fact, it wets glass. And so if you wanted to solder a piece of glass to a piece of metal, the thing that you would use would be indium. And in fact, it's used for a lot of glass seals in electronic devices. You use indium as a seal in the glass. But if you move up into the temperature scale now, you're going to find that you will find the lead-tin solders in a temperature region here. You go on up in the temperature and just find the rest of the materials, and they have very much higher melting points. But anything that's above that, we would be able to solder with a lead-tin solder, right? Just look on a temperature scale, and if I am joining anything that's above this with one of the materials that's down below, I'm going to be doing a soldering operation, particularly if the temperature of the solder is at a very low temperature. Well, suppose I want to, say, join together two pieces of steel, which would have a melting point way up here, and I want to make a junction that I'm going to use at a temperature above the lead-tin solder. Then I wouldn't use this. I use another kind of a soldering technique. Actually, it's called brazing, and I would use a material that's higher than solder in its melting point, but lower than the steel. But that brazing material, that brass, would have to have the capability of wetting the steel. And if it wets the steel, then we can join the two pieces together. Well, most of the solders that we are used to, in fact, the word solder to most people means a lead-tin alloy. And this is the diagram, the lead-tin diagram. And we find that we have a solid solution with the lead, which is the alpha solid solution over here, and a solid solution with the tin, which is the beta solid solution over here, and we have the eutectic. Now, if you were going to design a solder, if you had to select a solder, and you say, I want to go to the lowest temperature possible to join this material together, otherwise I might damage the material, then what you would want is a eutectic solder, and it would be a solder that would have that particular composition. If you wanted to solder a material and you had to play around with the junction a whole lot, you may want something that has a big distance between the solidus and the liquidus temperature, you may want a solder that's way over there. So in effect, when I was telling you earlier about the plumber wiping a joint, he was soldering two pieces of lead together with a material that melted in a range like this, and so he had a big melting range. But you may want to solder, say, some electronic components together, and you want to have that range narrow, and you don't want to spend any more money than you have to for the solder. And actually the material on this end costs well over $7 a pound. The material on this end is down in cents a pound, say 30, 35 cents a pound. And so you'd take a solder that looks like this, and you'd have a melting, beginning of melting here and an end of the melting there, a short range. So when the material looks like it's solid, it would really be solid. You wouldn't be tricked and take your hand away from the wire too quick and have it give you a little crack or a hot crack in your junction. So generally, a metallurgist, if he's asked a question about soldering or brazing, the first thing he thinks about is going to be the thermal equilibrium diagram between what you're going to use as the soldering material and what's being soldered. And so the solder series then describes for me what most people are thinking about when they're talking about soldering. Well, if we move into welding, welding is going to be the situation now where we're going to depend upon joining the two materials by melting a part of the parent material, the material that we want to weld together, the parts we want to weld together, so that we take the molten material from the two pieces that we want to weld together, make a common pool of them, and then allow it to solidify. Now this sounds so simple it isn't funny, but we generally have a problem. If you take two pieces of material and put them together, you cannot get them exactly, tightly together, and so there'll be a tiny little gap in between. If you melt the metal and cause it to be one pool of molten metal, then what's going to happen is, as it solidifies, we're going to have a shrinkage cavity. It's going to be thinner in section than it was to start with. So we generally use a filler material. And all of the welding that's involved in gas welding and arc welding generally involves a stick or a piece of excess material that we're going to use as a filler material to fill in this particular gap. Actually, there are many different types of welding, but they fall broadly into just three classes. And one class is gas welding, and I'll talk about that in a moment. Another class that we have is arc welding, or these are fusion welding processes, by the way. In both cases, we're going to have a molten zone. So in arc welding, we have a molten zone. And then we have resistance welding, where we essentially pass a current through the material at such a level of current density that the material is melted where the resistance is high, where we bring the two materials close together and we cause it to melt into a little button, but it's still a molten zone, and then it fuses back and we have a weld performed.
Joining metals involves using mechanical fasteners such as bolts or rivets, or continuous processes like soldering, brazing, and plastic or solid state or fusion welding. Soldering involves wetting parent metal surfaces with low melting temperature material that is miscible in the molten state with the parent metals. Brazing is similar to soldering, but it occurs at higher temperatures and involves metals with higher melting temperatures. Fusion welding involves melting a portion of the parent metal and uses a filler metal to prevent a shrinkage cavity upon cooling of the weld. Fusion welding processes include oxyacetylene gas welding, arc welding, and resistance welding.